for this question, right, it's about teaching you about the table of outcomes. All right, so an ordinary die, right, one red and one blue, each to be rolled once. So events A and B are defined as follows, where event A is that the number on the red die is a 5 or 6. Event B is where the sum of the two numbers is equal to 7. So you notice that what we did is, because there are two events happening back to back at the same time, actually, and we have so what we do is we represent them using a table of outcomes, with the red die representing by 1, 2, 3, 4, 5, 6, and the blue die giving 1, 2, 3, 5, 6 as well. So I want to find that the probability that the number on the red die is a 5 or 6, and the sum of the two numbers is equal to 7. So what's the probability of B intersect C? B, the conditional probability of B given C. Alright, so this question is asking you on conditional probability. And if you have studied as you have been taught, the conditional probability can be seen in two different ways. One is you can look at it as the probability of B given C can be the same as the probability of B intersect C over the probability of C, or this can be the same also as basically the number of outcomes where B intersects C over the number of outcomes of C. Alright, so let's look at B intersect C. So we want B intersect C, it means that we want the sum of the two numbers to be equal to 7, and we also want at least one of the two die to show a 5. So we'll need these to both happen at the same time. So if we were to look at the table of outcomes, you can see that if I want the sum of the two numbers is equal to 7, that will probably be all of the numbers that we have over here. And if we want, that will be my B, right? So that will be my B. Basically, this is my B. And if I want at least one of the two dice to show a 5, that's like basically all over here. I mean, all the two dice show a 5. You can see that it's basically here, right? Two dice show a 5. Okay. At least one of the two dice shows a 5. At least one of the two dice shows a 5. Okay. So it can also be 5, 5 even. Alright. So the thing is, if I look at B intersect C, I can see that basically there can only be two possibilities. That is either this and this. Alright, there are only two of them, which is over here. Okay, only these two. Okay, but however, if I were to look at the total number of ways that C can happen, C can happen actually in so many ways. If I look at C, C basically is the number with at least one of the two die must show a 5, right? So it can be this, it can be this, right? So all of this includes the fact that each of the two die must show a 5. So there are actually total of 11 ways that I can have C to happen. There are a total of 2 ways, only 2 ways for B intersect C. So if I were to do a count, this would be the 2 ways for B intersect C and 11 ways for C. Alright, and next, okay, I want to show that A and B are independent. This means that if I were to look at part B, what I'm trying to show is I want to show that the probability of A intersect B, so this is just a formula that we need to follow, is equals to the probability of A multiplied with the probability of B. Okay, and probability of A intersect B, as we see, is basically I want the die to be a 5 or 6, and I want the sum of the two die to be equal to 7. So if I were to erase what I have earlier, I want the sum of the two die to be equals to 7. So sum of the two die will be equals to 7. If I look carefully, the sum of the two die to be equal to 7, that will be over this part. And C is where at least one of the two die to show a 5. So sorry, this should be A intersect B. So A is I want the red die to be a 5 or 6, so there can only be this part. Okay, so this is my actually my A lah. This is actually my A. Okay, so probability of A intersect B, you can see that there's again only two possibilities, which is these two again. Alright, it's a total of two, basically 2 out of 36. Alright, total 36 outcomes. Probability of A, however, probability of A multiplied by the probability of B, as you can see, probability of A is basically equals to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 out of 36, which is 12 out of 36. Okay, and probability of B is basically what we saw earlier, 1, 2, 3, 4, 5, 6. Let me just use 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So it's a total of 11 out of 11. Sorry. 11 is 11. 1, 2, 3, 4, 5, 6. And when the sum of the two die is equals to 7. No. Sorry, I got it wrong. This is not my B. My B is actually over at this side, right? Where I need the sum of the two numbers to be equal to 7. So it's only 1, 2, 3, 4, 5, 6. There are only 6 ways. So instead of 11, it should be 6. Okay, so I'll just verify. Over here, the probability of A multiplied the probability of B would just be 12 over 36 multiplied with 6 over 36. And it actually indeed gives me 1 over 18. Alright, which is the same as the probability of A intersect B. Okay, so since they are actually equal, we can conclude that A and B are independent. Alright, so we can write it down, since probability of A intersect B is equals to the probability of A multiplied with the probability of B. Alright, so this is the important definition for concluding independence. The moment you are asked to compute or show independence, you must be able to write that the probability intersection is the same as a product of the two probabilities involved. Okay, hence A and B are independent.